Buffer solutions. They're pretty important. One example of them is in your bloodstream. The pH level in your blood has to be regulated at a very tight range, just between 7.38 and 7.42, in order to survive. And the way your body maintains this pH level is through a mixture of carbonic acid and bicarbonate base in your bloodstream. So that when there are too many H+ ions, the bicarbonate base picks up the H+ ions to form carbonic acid, and when there are too few H+ ions, the carbonic acid splits to supply more H+ and form bicarbonate base. In both cases, the solution of carbonic acid and bicarbonate base together work to effectively neutralize any pH change, keeping the pH within this very narrow window. And that is the essence of a buffer solution. If you're watching this video, chances are it's because you're deeply confused with buffer solutions, or your chemistry teacher has decided to put on this video for you, or both. But the very first thing you need to know to crack open the deep dark secrets of buffers is to know just what a buffer solution is. A buffer solution is an aqueous solution that will have very little change in pH when adding a strong acid or base, and it is formed when the solution has an equal concentration of a weak acid and its conjugate base at equilibrium. In other words, if a solution has an equal amount of weak acid HA and its conjugate base A- at equilibrium, then the pH of the solution will change very little if you add H+ or OH- to it.
In fact, let's test it out. So here I have a buffer solution of acetic acid and acetate ion, and here I just have pure water. Now notice that the pH meter here says 4.4 for the buffer solution, and here the pH meter says 7.2 for the water. Now let's see what happens when you add a few drops of NaOH to each solution. So you'll notice now that the pH of the water is now 8.7, while the pH of the buffer solution is pretty much 4.4, it's still 4.4. In fact, I'll add a few more drops of NaOH. 2, 3, 4, 5, and the pH remains at 4.4. 6, 7, 8, 9, 10. Okay, I've stopped counting the drops, but you'll notice that even with that huge amount of NaOH, the pH remains just at 4.8, and keep in mind that it was around 4.4 earlier. So yeah, that's pretty much a buffer solution. It resists a change in pH. Ooh, look, it's a transition!
To make a buffer solution, you have to have an equal concentration of an acid, HA, and a conjugate base, A-, at equilibrium. There are two ways to do that. One is by mixing a solution of a weak acid, HA, with a solution of a soluble salt containing its conjugate base, such as NaA. The other way is by titrating a weak acid halfway with a strong base, or alternatively by titrating a weak base halfway with a strong acid.
Let's look at the first method. Here I have 100 milliliters of 0.1 molar acetic acid, or H2H3O2, and here I have 100 milliliters of 0.1 molar sodium acetate, or NaC2H3O2. Because acetic acid is weak, most of this solution is just undissociated H2H3O2. Meanwhile, sodium acetate is highly soluble in water since it contains the group 1A ion sodium, meaning what's in this solution is mostly dissociated Na+ and C2H3O2- ions. Now let's put the two solutions together. And there you have it. You can't see it, but now I've officially made a buffer solution of acetic acid and sodium acetate. In this beaker is H2O, a near equal concentration of acetic acid and acetate ion at equilibrium, and the dissociated Na+ ion. The Na+ ion does essentially nothing in this solution, and since acetic acid is a weak acid and acetate ion is a weak base, neither one of them reacts much with H2O to form either H+, OH-, or its conjugate.
Now hold on, you might have heard that strong acids have weak conjugate bases, so how exactly does this weak acetic acid also have a weak conjugate base? Well, the answer relies on equilibrium constants Ka, Kb, and Kw. Ka refers to the constant when an acid reacts with H2O to form its conjugate base and H3O+, Kb refers to when a base reacts with H2O to form conjugate acid and OH-, and Kw refers to when H2O dissociates into H+ and OH-, which is 1 × 10⁻14 at 25 degrees Celsius. Remember that Ka and Kb refer specifically to H2O being a reactant, not H+ or OH-. In order to get a Kb value, you divide the Kw by Ka, and to get a Ka value, you divide the Kw by Kb. In this case, the Ka for acetic acid is 1.8 × 10⁻⁵, which makes it a weak acid since the Ka is less than 1, and the Kb for acetate ion is the Kw over that value, which is equal to 5.6 × 10⁻⁻10, which also makes acetate ion a weak base with the Kb less than 1, and a strong acid such as HCl has a Ka of 1.3 × 10⁶, meaning the Kb for Cl- is 7.7 × 10⁻21, which means that strong acids produce very weak solutions. But it's important that in a buffer solution both HA and A- be weak, meaning these Ka and Kb values have to be less than 1. You can't make a buffer solution with a strong acid because with a Ka more than 1, the acid would more favorably react with H2O to create an unequal balance of the acid and conjugate base at equilibrium. However, if both the acid and its conjugate base are weak, neither one of them will want to react with H2O to shift the reaction, which means that an equal concentration of Ha and A- is much more likely to be maintained. Now let's move on to the second way to make a buffer solution, which is titrating a weak acid halfway with a strong base, which I'll show on camera.
Here I have a 0.1 molar solution of 50 milliliters of acetic acid, and here I have a burette containing 0.1 molar NaOH, which is a strong base. Now since both have the same concentration, it should take 25 milliliters of NaOH to create that buffer solution. I've also added some indicator that will turn red at 50 milliliters NaOH, and right now the pH of the solution is at 2.7. Now let's start titrating.
First off, with no NaOH titrated, what I have in here is mostly undissociated H₂O since acetic acid is weak. The pH of the solution starts off at 2.7, less than the neutral 7 due to the presence of acetic acid, which still forms more H+ at equilibrium than water does despite it being a weak acid. Remember that because NaOH is a strong base, what's in the burette is mostly Na+ and OH- ions dissociated from NaOH. As I add NaOH from the burette into the solution, the new OH- ions pick up the H+ in the H₂O to form H2O and C2H3O2-, resulting in less HC2H3O2 and more C2H3O2-, while the Na+ ion just sits in the solution, silently observing everything. As I keep titrating, the ratio of acetic acid to its conjugate acetate ion gets closer to 1:1, meaning we're getting closer to a buffer solution and the pH increases along the way. Now 25 milliliters NaOH is a special moment because that means the concentration of NaOH is exactly half the concentration of acetic acid, also known as a halfway point, which means that when the OH- reacts, the ratio of acetic acid to acetate ion ends up exactly 1:1, which is why the halfway point of a weak acid strong base titration gets you a perfect buffer solution. Also notice on the graph that at the halfway point, the graph is moving near horizontally, meaning the pH changes the least at the halfway point, which is another key component of a buffer solution. And with more NaOH added afterward, the concentration of acetate ion ends up higher than the concentration of acetic acid. So before the halfway point in a weak acid strong base titration, the concentration of acid is higher than the concentration of conjugate base, while after the halfway point, the concentration of conjugate base is higher than the concentration of acid. When I have 50 milliliters NaOH, that means an exact amount of OH- reacts with Hc2H3O2, which is also known as the equivalence point in the titration. Now what's left in the solution is all the Na+ ion, which still does nothing, the acetate ion formed, H2O, as well as tiny amounts of H+, OH- and acetic acid. The pH is higher than 7 at the equivalence point because the acetate ion reacts slightly with water to form acetic acid and OH-, which makes the solution slightly basic. Beyond the equivalence point, since there is no more acetic acid to react with OH-, we end up with an excess of OH-, which increases the pH with more NaOH added. And that is a titration of a weak acid with a strong base. You can also titrate a weak base with a strong acid to get a buffer solution, which results in this graph. Notice how the weak base graph is just the weak acid graph flipped upside down, and at the equivalence point the pH is less than 7 as opposed to more than 7. In a weak acid strong base titration, the pH of a solution at any moment before the equivalence point can be found using the Henderson-Hasselbalch equation, where the pH of a solution is equal to the pKa of the acid plus the logarithm of the ratio of the conjugate base to conjugate acid. Pause the video here if you want to see the calculations to get there. In a buffer solution, the ratio of a conjugate base A- to acid Ha is exactly 1:1, meaning the logarithm of the ratio is equal to 0, which means the pH is equal to pKa plus 0, therefore in a buffer solution the pH is equal to the pKa. Here, since the pKa is equal to the negative log of Ka, the pKa of acetic acid is equal to 4.8, meaning at the halfway point, the pH is equal to 4.8. And finally, despite not making a buffer solution, it's also important to identify a graph of a strong acid also titrated with a strong base, such as HCl and NaOH. Because both are very strong, they both dissociate into H+, Cl-, Na+, and OH-. The more NaOH you add, the higher the pH becomes as the OH- in NaOH reacts with the H+ in HCl to form H2O, while the Na+ and Cl- ions just observe again. At the equivalence point, an exact amount of NaOH has reacted to neutralize the solution of HCl, meaning at the equivalence point in a strong acid strong base titration, the pH is equal to 7. After that, you just have an excess of NaOH, making the solution more basic and at a higher pH.
And so, that's it. You did it. You've learned the deep dark secrets of buffers, sorta. If you're still confused, here are the parts that you actually need to know.
A buffer solution is resistant to a change in pH. The best buffer has an equal concentration of a weak acid and its conjugate base. There are two ways to do that: mix a weak acid by a salt of its conjugate base, or titrate a weak thing halfway with a strong thing. Titrating a weak acid by a strong base gets this graph, and titrating a weak base with a strong acid gets this graph. The equivalence point is where you've titrated an equal amount of the strong thing, while the halfway point is where the actual buffer solution is. The equivalence point always goes past the pH 7 line. By the Henderson-Hasselbalch equation, the pH is equal to the pKa of the weak acid at the halfway point. And finally, this is the graph when you titrate a strong acid with a strong base. You cannot create a buffer when titrating a strong acid with a strong base because there is no plateau at the halfway point, meaning the pH still substantially changes at the halfway point when adding an acid or base. At the equivalence point, the pH is exactly equal to 7, while titrating a weak thing with a strong thing is never 7 at the equivalence point.
And I'm done. Goodbye. Just leave.